deliver lectures in this particular session. So I again welcome all the participants, and as already introduced, basically I belong to IIIT Allahabad, which is an institute very similar to IIIT Jabalpur. And basically we have a computer vision and biometrics lab here. And we have 5 faculty members which are currently associated with this CVVL, that is CVV lab. And these are basically the sponsors who fund our research or even our professional activities like conferences or short-term courses. And at present, we are having some ongoing projects where 3 international projects are being executed. That is Indo-German, which is funded by DAD of DST, Indo-Slovenia, and Indian Taiwan project, which is funded by Gita. And even a project is being funded by Ministry of Home Affairs. We also used to conduct some events in terms of conferences and short-term courses. And in fact, one of the summer school, which is again sponsored by IEEE Computational Intelligence Society, it is lined up and going to be organized from July 17 to 21. So if anyone is interested or anyone known to you who is interested, they can apply for this particular course. And here is the website for this particular course. If you want, you can just message me. I will send you further details regarding this. So now without further delay, let's come to the topic. And as we are going to discuss neural network, and when we are discussing the neural network, then we should start basically with a very simple classification problem. And because we know that this neural network has been designed in such a way that it can better deal with the complex data, and where we can have nonlinear separability, means the simpler classifiers where it can fail, neural network can work very well. So then how this neural network is actually evolved over the time and how it has made use of the basic classification techniques. So that's what we are going to first have a look. So suppose if we want to do the classification, and for better visualization perspective, we can consider images as the example. So suppose if we consider image classification or image categorization. So what is in general classification problem? We are having samples of different categories, and then we will make use of those samples to train any model or any classifier. And when we get a new sample from these categories, then we want to test how well this particular model which we have trained is performing on the new sample. So basically, training means what? Training means we want to find out a function where if we provide any sample as the input to that function, then that function should be able to return as the class label. So that's what is very basic understanding of this classification. What will be that function? That this function could be anything. So based on the function, we can have a different classifier. We can have nearest neighbor classifier, we can have support vector machine, we can have neural network, linear classifier, or even nowadays convolutional neural network or any other such type of networks we can have. But ultimately, we want to provide sample as the input, and our model should be able to predict the class label for that particular sample. So this is a very simple classification approach. If we talk about statistically, then we can write y is equals to fx, where x is our input that we are providing to our function f, and we want to predict output y. And obviously, when we want to predict output y, then at the training time, means we are dividing our data into at least 2 parts. Usually it is divided into 3 parts called training, validation, and testing. For simplicity, let's consider 2 parts, training and validation part. So when we divide our data into the training and validation part, then we also make use of the labels which is available with us for the training part. So for example, here, if we consider this, suppose if this is our training data set, then we will say that, okay, The first row is all these samples are coming from the same category. So let's gives this all these samples to label 1. Next row, because they are coming from the same category, we can give next label, suppose 2. So like that, in this example, we can have 6 different labels because we are getting the samples from 6 different categories. So what happens, we will get the output here. Now this output is the class label. So for simplicity, we can consider the labels also as the number, like 1, 2, 3, 4, where 1 is the first class, 2 is the second class, 3 is the third class, like this. So what we want during the training. So during the training, we are having a training set. We can now assume training set is labeled as x1, y1 to xn, yn. What does it mean? It means that in the training data or in the training set, we have total n samples, which is represented by x1 to xn, and the labels of these samples are given by y1 to yn, where this y1, y2, y3, this could be any one of the labels of our dataset based on this example xi is coming from which category. So what we want during training, we want to make use of this data that this is the sample and it belongs to this category. We want to make use of this information to find out what should be this function, such that if we provide x1 to xn as the input to this function, then it should produce the output y, which should be very similar or which should be same as y1 to yn. If it is not same, then there will be error. That error we would like to measure, and based on that error, means that is actually kind of a feedback that we are getting for our function f, that our function, how well it is performing on the training set itself, and that is the feedback, and we want to make that performance better, and that's how we will do the changes in this function f to find out better and better function. And ultimately, once we are convinced based on certain criteria that we have achieved now good performance on our training set, then we can say, okay, now basically whatever function we have, that is a good function, and even it can be utilized for the testing purpose. And uh, even sometimes, not just based on the training, we also try to find out the performance based on the validation set, and then we decide based on the validation set that what should be our final function, that is our trained model. Now this function, either we say function or trained model or network, all these are going to be basically the similar notations that actually we are representing to this model, which is which can be even a parametric model or non-parametric model. So mostly we are going to have a look here for the parametric model, because neural network is a parametric model. So what we do at the testing time, so at the testing time, we assume that we get the data, and for that data, the suppose if labels are not known, then also because we know that what is the function f, so we can find out its label. And for the test set that we have in any data set, we also know what is the label for those test set, but actually we don't use that label for any other purpose except only judging the performance of the model on our test set. Means we will take the data from the test set, suppose x is the sample, we will find out what is the label, and then we could do the comparison with the actual label of that example, and then based on that we find out what is the performance of this trained model on that test set. Okay, so now let's try to visualize this function f through a very simple classifier, which is called linear classifier, because later on we find that this neural network is also working very similar to this linear classifiers, and it is some sort of extension of the linear classifier. And again, for simplicity, let's consider only two class problem, means we are having the samples coming from only two categories. Here you can see there are some blue squares and there are some red circles. So basically these blue square and red circles, they are representing the sample coming from different categories. So this is category 1, this blue one, and red one is category 2. So now what is this sample? This sample could be anything. Suppose if we have an image, then this is the representation of the image in some d-dimensional space. Even suppose if you are having the text, then we can have the embedding of the text in some d-dimensional space. So though you are seeing a red circle here, but actually this is a d-dimensional vector. It is called d-dimensional feature vector, and which is input corresponding to the that particular sample. So for example, suppose if we have an image, then a very simple vector that we can get for image is to just stretch the image into a vector. Means just if we just hold the top and left corner and bottom and right corner of the image and just stretch it, then it will become a single vector. So we can consider that vector as the input here for our model. So basically, in short, these data points that you are able to see here, they are basically the input feature vector for the samples represented in some d-dimensional space. So what we want to do with this data? Basically, we want to find out a classifier which can separate these two categories. Means using that classifier, we can say all these blue ones are at one side and the red ones are at the other side. So even we can visualize this into a two-dimensional space. If we consider two-dimensional space, then that linear classifier will become a simple line. So if you consider a two-dimensional space representation, then we can have a simple line in between these two distributions like this, and then we can have a clear separation between these two distributions, means these two categories. And because we know if we are having a line here, then we can figure out, given any point in the space, it belongs to which side of the line, left side or right side. And based on that, we can say this belongs to the category 1 or category 2. So even we can extend this to d-dimensional space. In d-dimensional space, this line will become hyperplane. So in d-dimensional space, where these data points are represented in d-dimensional space, we can have a hyperplane in that dimension. So how we can represent that hyperplane? We can represent that hyperplane as w dot x plus b, where w is the vector of the parameters and x is basically the different dimensions that we have. So for example, if we are having a two-dimensional, then we can simply write uh, uh, the equation of the line. For example, we are using y is equals to mx plus c. So similarly, we can extend it to d-dimensional. So there we can have w dot x plus b, where now this w is a vector of these coefficients or the parameters, and x is basically representing the different dimensions like x1, x2, and up to xd. So what happens once we know what is the equation of this hyperplane? Knowing equation of the hyperplane means what? It means that we know what is the coefficient values, that is w1, w2, and up to wd, and also this bias, which is b. So if we know what is the coefficients of these hyperplanes like these w's and b's, then for any given new point, saying it belongs to the left side or right side becomes very easy. Then what we do, we simply solve this w dot x plus b, because we know what is the coordinate of the new point, that is x1, x2, x3, and up to xd values, because we know it's d-dimensional feature vector of that sample. And we because suppose we have already trained model, and this is our hyperparameter, this is our hyperplane, means our classifier. So we also know what are the coefficients from w1 to wd. So then we can find out what is the sign of this w dot x plus b, and if this sign comes to the negative, then it belongs to the first category, otherwise it belongs to the second category. So this is going to be a very simple parametric model where we have the parameters, and these parameters are nothing but coefficients of these hyperplanes, that is w1 to wd, and this bias, which is b. So at the training time, what we want to do? At the training time, we want to figure out what should be the right values of these w's and b. And that's what, if we can figure out, then we get the classifier and we can utilize that at the test time. And we can extend this particular idea even for more than 2 classes. For example, suppose if we have 3 classes, then in that particular case, what happens? If we are having 3 classes, then we will have the 3 classifiers, and we can build a coefficient matrix or a parametric matrix, which is represented at W here. So now if you see this W matrix, it basically has 3 rows. So what is meaning of this 3 row? The first row represents the classifier for the first class. The second row represents the classifier for the second class, and the third row represents the classifier for the third class. It means that if we are having C number of classes, then basically we have to utilize C number of classifiers, and number of rows in this matrix W will become C. But that is not true for the 2 classes, because for 2 classes, we can just manage with the sign. So that's why only one classifier is sufficient to say the sign is positive or negative. But when we have more than 2 classes, then only sign will not be sufficient. Then we have to talk about the class scores for different classes. So that's why we have to consider that many number of classifier with respect to how many classes we have. So we can also think like this. The first row is the classifier for the first class, which will try to distinguish the first category sample from rest of the categories. Similarly, the second row here representing the second classifier, that is the classifier for the second category, will try to have all the samples of the second class at one side and samples of all other classes at other side. So then how we can get the class score? We have the sample image here, or any data that we are getting, and we represent that data into feature space. And suppose this is the feature representation of the data, that is 56 to 31, 24 to. And what is the dimensionality of the feature? That becomes the number of columns in our W matrix, that is also called a weight matrix or parameter matrix. So now if you see the number of columns here, it is 4. Why? Because at the end we need to perform W dot X, and that W dot X also we have to perform in neural network. That's what we will see. So in this W dot X, what we are doing, basically W, suppose if we consider the first row here, then first row is the classifier for the first class, and X is our data. If the dimensionality of W and X both are same, then only we can perform the dot product. So that's why the dimensionality means the number of columns in this W and dimensionality of our data should be same. Then only we can perform W dot X. And this is the vector B. So we will add this vector B after doing this W dot X. Because we have 3 rows here, so we will get 3 class scores. And actually the first score is the class score for the first category, suppose that is cat. And the second one is the class score for the second category, suppose that is dog. And third one is the class score for the SIP category in this particular example. So now what happens at the training time? What we need to do at the training time, we need to figure out what should be the right values of this W and B. And that's where basically optimization also comes into the picture, that okay, how to find out. Now it becomes an optimization problem, and we will see later on that we can utilize gradient descent optimization technique to figure out that what should be this right set of values of W and B, and how these values are computed. Based on that, we will have different classifiers, like support vector machine will have different strategies, neural network will have different strategies. But nowadays this gradient descent optimization based techniques are very common to solve this particular problem. So and here is the visualization of these classifiers. So what happens, suppose if you are having a classifier for airplane category, so what it will try to do in basically feature space, it will try to have all the samples of airplane at one side and samples of all other categories at other side. Similarly for other categories also, like car or deer or any other category. Okay, so we are not covering nearest neighbor classifier here because that is the simplest classifier, and I hope that all of you would be knowing that. But what are the some benefits and drawbacks of linear classifier? So first of all, this is a parametric representation. So parametric representation is going to be good because basically we can have a powerful classifier, and it will be very fast at the test time, because at the test time we don't have to do much task. What only we have to do is to find out this W dot X plus B, and based on that we will get the class scores, and for which class we are getting the highest class scores, we can assign that particular category to given sample. But there are some downside, like how we will train this linear function, how we will find out the right set of values of these w's and b's. That's what is going to be challenging. And what will happen if data is not linearly separable? So what we are going to do now, we are going to basically see these both downside of this linear classifier and how we will tackle this. Means how we will train this linear function using this gradient descent optimization, and how what we should do such that even if our data is not linearly separable. Now, what is meaning of not linearly separable? So here you can see in this example, the blue ones are very clearly separated from the red ones, and we can find out a hyperplane in between, which can basically distinguish these two very easily. But what happens, suppose if these red samples even comes at the left side, or even blue samples goes to the right side, means we cannot find out a linear classifier or a linear hyperplane which can separate these two categories. Then this linear classifier will basically fail in that particular situation. And that's what happens in reality. In reality, the data set that generally we get to deal with, they are not linearly separable. They are basically complex data. So how we can do, how we can solve this problem, and that's where basically this neural network will come into the picture. However, coming to the first part, means how we will train the linear classifier, though we will have more discussion on the optimization, but a very basic strategy is the gradient descent optimization technique. And what happens in the gradient descent optimization technique, we we start with the random values of these w and b. Means before starting, we initialize these w's, means the parameters or coefficients, with the random values. And after initializing with the random values, then we will basically do the forward pass of the network with some samples, and we will compute the loss. And based on getting the loss, we also compute the gradient of our loss function with respect to all these parameters. And using that gradient information, we update these values, and that is called gradient descent optimization technique. But a very important thing here is we should have some objective function, or we should have the some loss function ultimately that we would be minimizing through this entire optimization. So what will be that loss function? And for classification technique, or for classification problem, in recent days, though there are many classifiers, many objective functions exist, but in recent years, even after deep learning, softmax classifier is very common, and it is being used very heavily. And blindly people are basically using this softmax classifier, using cross entropy loss as the by default choice for basically training of these models for the classification purpose. So let's have a quick look over this softmax classifier, that what is this softmax classifier. So if you again remember, if we have any classifier, either it is simple classifier or even neural network, in all these cases, what happens at the end, we get the class scores. So suppose if we are having C number of classes, then we get C number of class scores. So when we get the C number of class scores, so let's represent these class scores as S1, S2, S3. And once we have these class scores, then what we will do, basically we will project that class score in the exponential space. Means we will compute e to the power of those class scores. And why we do that? Because ultimately what we want to do, we want to convert the things into the probability, but even we can get a negative class score. And we know that in the probability, we do not have the negative term. So that's why what we do, we basically project the class scores into the exponential space, because we know e to the power will always give you the positive number. So in that particular case, everything will be projected as the positive number. So all negative numbers will be restricted between 0 and 1, and all positive numbers will become even higher. And another benefit of doing this, if there are some ambiguity in class scores, means for example, suppose if two class scores are very if two class scores are very close to each other, but once we project that into the exponential space, then the separation between those class scores will increase in the exponential space. So it will also be beneficial to avoid the ambiguity. So after converting into the exponential space, now we get the all class scores as the positive numbers. And then what we do, we find out the summation of all these class scores and divide the class score of the correct class by the summation of the class score of all other classes in the exponential space. And that's what is basically the probability, because if we divide e to the power syi, yi is the ground truth label, means that is the correct class label. So syi is the class score for the correct class. Means suppose if you are giving one example right now from the cat category, then what is the class score for the cat category? E to the power of that is going to be this number. And what will be in the bottom? Summation of e to the power of class score for all the classes when input is that particular sample of the cat. Once we get the probability, then what we do, we find out the negative log likelihood of that probability. And if we get the negative log likelihood of that probability, then this is going to be the loss. And why this is going to be loss? Because suppose what happens, suppose if we get a sample, and if we get a sample in such a way that these class scores that we are getting very high class score for the correct class, but the class score for the incorrect classes, they are very small number, tends to suppose negative infinity. Then what happens when we compute the probability, then this probability tends to 1. Why probability tends to 1? Because the class score for the correct class is very high and class score for all other classes are very low. And that is a good thing. It means that whatever W and B's we have, they are basically very right values, and they are doing very well on this particular example that we are feeding right now, because it is giving very high class score for the correct class and very low class score for all incorrect classes. And that's what we want. So in that situation, what happens, this classifier should not do any penalization, and that's what will happen, because this probability tends to 1. When this probability tends to 1, then in that particular case we know that what is going to be the log 1, that is going to be 0. So that's why it means that this loss will become 0 when the classifier will provide very high class score for the correct class and very low class score for incorrect classes. It means that our classifier is already good, so loss will become near to 0. But what happens when classifier is not doing well at the training time? Means for any example, it gives us very small class score for the correct class and gives higher class score for the other classes, that is incorrect classes. When it happens in that scenario, this probability that we will get here, it will be close to 0. And when this probability is going to be close to 0, then log of 0 will tends to negative infinity. It means minus log of 0 will tends to positive infinity. It means when our classifier will be doing worst, in that scenario loss will be very high and it tends to the infinity. And that's where basically our model will learn, because it will be penalized very heavily. So it has to learn, it has to basically change the weights, change the parameters W and B's in such a way such that in future this class score should be better for the correct class. So softmax loss generally has two parts. One is called the data loss, which is this particular equation, and another one is regularization loss. Right now, we are not going in detail regularization. We will go in the second session where we will discuss about the generalization. So here we can have a very quick example. So suppose if this is the W and we have xi as one of the input and b is given at present, suppose these are the values of W and B, then what is going to be the cross entropy loss using softmax classifier? And suppose our example is coming from yi is 2, that is the category number 2, and here category is basically 0 for the first row, 1 is for the second row, and 2 is for the third row, means it is coming from the third class. So we get the class scores. These class scores are minus 2.85, 0.86, 0.28, corresponding to 3 different classes. Then we take the e to the power of this in exponential space and do the normalization. And after doing the normalization, what we do, we find out the negative log likelihood of the probability for the correct class. And what is the probability for the correct class here? Because it comes from the category number 3. So probability for correct class is 0.353. So minus log of 0.353 comes to 1.04. So this is going to be basically the loss for this particular example, which is xi at present when w and b are having these values. Okay, so is there any question from anyone so far? Because now we will move to non-linearity and slowly towards the neural network.
Students, please feel free in asking questions because you have got an opportunity. You should not miss it.
Okay, so as I mentioned that we have this linear classifier and we are getting some feature representation of our input to be given as the input to this linear classifier. And this is called the shallow approach. So shallow approach means we are having only two steps in this approach. In the first step, somehow we find out some feature representation. That feature representation, how we are finding, sometimes it may be dependent upon the user. That user is thinking, okay, if we can extract this information, then it will be useful. And in the second step, we utilize this linear classifier. However, nowadays we are having this deep approach. In the deep approach, what happens? We pass our input directly to a network, and that network will have different layers. And these different layers will be extracting the features, and the extraction of the features will happen automatically. Means now we don't have to say that, okay, extract color feature or extract texture feature or extract shape feature, or if you are having the textual content, then you are basically going to extract that, okay, these two words are if you're familiar with bag of word model, you are extracting bag of word feature. So all these things we don't have to be bothered right now. So what we have to bother, what should be this layer, and this layer should figure out automatically that what features to be extracted. And this is going to be basically the deep approach. And in this deep approach, we will have basically the linear layers, and in between these linear layers, we will also have some non-linearity layers. Because if we are having non-linearity layers, then only we can project our input from a we can project our input in such a space where it can become linearly separable. So what is meaning of this linearly separable? If you see here at the left side, so we are having these two categories, again, blue and reds, but they are not linearly separable because we cannot find out any hyperplane, a single hyperplane, which can divide these two categories. But if we do some transformation, so for example, all these points are transformed in the right side figure here, we can see in such a way that all these blue ones have now gone at one side and red ones have gone at other side. So this is in some higher order space representation. For example, if you see the left side, this is 2-dimension, but if you see the right side, this is 3-dimensional space. So when we are going in higher dimensional space, then we will get this flexibility to convert our data which was not linearly separable, it may become linearly separable. But then question comes that how we will figure out that transformation function. So that's where basically this neural network will be very useful, because it can automatically figure out this transformation function. So now here you can see in the right one, we can have a hyperplane that can basically separate these two categories. So now we can write even this step, means this transformation, we can write as a kernel. And if you are familiar with support vector machine, right now I'm not going in very detail of support vector machine. If you are familiar of support vector machine, there is a kernel concept of support vector machine. What that kernel concept of support vector machine does, it basically transforms the data into the using some nonlinear function. Actually, we don't transform. We have a kernel trick there. Using that kernel trick, it is performed. But ultimately, what is going to be benefit of doing this? It will be equivalent of transforming our data into some other space using some nonlinear transformation, and then using the transformed data for our final output. So here we can see we have x1, x2. Using x1, x2, now we can basically represent in some more dimension. For example, we had, suppose our input had only 2 dimensions, x1 and x2. But now we can have x1 square as 1 dimension, x2 square is another dimension, root 2 x1, x2 is another dimension. Like that, we can have many dimensions. And now it is our choice that how many dimensions we would like to have. So even the same thing is also applicable in case of the nonlinear support vector machine. So what happens? But in case of the nonlinear support vector machine, the kernel that you are picking is a fixed kernel. Means this transformation that we are going to have, the data that we are transforming using a kernel function is a fixed transformation. So, and that's where basically it also becomes a problem for the practitioner, that if you would like to use support vector machine, which kernel to follow. Then people used to do basically used to try different kernel functions, and then they see that okay, which one is performing better, and based on that they pick, okay, for my problem this particular kernel is performing well. But there are many kernels. How many kernels basically you can hit and try? So that is going to be the problematic thing. So that's where what happens, suppose if we extend this particular concept in such a way where these transformations that we are defining, suppose if these transformations are not fixed transformation, just 1 second. Okay, sorry for this interruption. So there is a question, what is SVM? So SVM is support vector machine, because we are majorly going to focus neural network, so I'm not going deeper there. Support vector machine is basically, if you just consider this diagram of linear, yeah, this one. So what happens in support vector machine, basically we try to find out this hyperplane in such a way that it should maximize the margin. Now what is the margin? If we get the parallel hyperplane which is passing to the nearest sample from both the categories, then what is the distance between those hyperplanes? That is called margin. So support vector machine tries to maximize that margin. Based on that, it finds this hyperplane. So support vector machine is also a classifier, which, because we can have infinite number of these hyperplanes which can separate these two categories. So out of infinite number of such hyperplanes, which one to pick? So support vector machine picks based on a maximum margin criteria. So that's why sometimes support vector machine loss is also termed as max margin loss. So you can further study it in detail. Okay, so what we were discussing, that we can have this non-linear transformation of our data, but in case of support vector machine, usually that is fixed transformation. So what we can do now, instead of having a fixed transformation, can the transformation itself be decided by the network based on what is the performance of the network on the training data on which we are training the model. So basically, and also why to have only one layer of transformation? Even we can have this transformation multiple times to be applied, and that's where basically we can have a layered approach where we can apply these transformations in the multiple layers, and that basically gives the rise to this deep approach where we have this stack of multiple layers. It can be linear and even non-linear, and this is basically linear predictors, which is called perceptrons or even neurons, which is interspersed with non-linearities. So now let's come to a perceptron. So what is the perceptron? So perceptron is the smallest building block in any neural network. And very interestingly, this perceptron is nothing but what we have just seen in the linear classifier. If you recall what we were doing in the linear classifier, we have some data. Based on the data, we want to find out a hyperplane. Right now, I'm considering a two-class problem for simplicity. We want to find out a hyperplane which is having the parameters w1 to wd such that if we perform w dot x plus b, if we perform w dot x plus b and consider the sign of this, then we can classify into one class or other class. In case of the multiple classes, it will gives us the class score. So the same thing, if we can represent in a pictorial form. So here you can see we are having the input. Input is d-dimensional, so it is represented as x1, x2 to xd. And what we do, suppose we are passing this input to a perceptron, and this perceptron will have the weights associated with different links or different connections that it receives from different dimensions of the input. So W1, W2, W3, WD. So how many number of weights we will have? That depends upon how many number of connections we have here. And number of connections will be governed by the number of inputs that we have here, means dimensionality of the input. And at the end, what this perceptron will do? This perceptron will compute the weighted sum of these inputs, means x1 into W1 plus x2 into W2 plus x3 into W3 up to xd into WD. And basically this is nothing but if we consider x1 to xd as a vector and represent by capital X, and w1 to wd as a vector and represent by capital W, then actually we are doing w dot x. That's what we were doing in case of the linear classifier. And once we do the w dot x, even we can have a bias term here also. We can have another input receiving as b. So we can get this w dot x plus b. And after that, we apply a non-linearity. For example, in the earlier case, we applied a sine function. So that sine function itself is a non-linear function because it gives you the output only in the binary, either basically negative or positive. So this output of a perceptron now can be represented as Z W transpose X here, because this is being represented as a matrix multiplication. And even we can have a bias term, then it will become W transpose X plus B. And G is basically the non-linearity in this case. And these non-linearities are also termed as activation function in the terminology of deep learning. And there are many popular activation functions which are being used nowadays. And the most popular is the ReLU. But there are other activation functions also like sigmoid, tanh, and ReLU. Basically, these are the nonlinear functions. And most of these functions are trying to basically transform the inputs in between 0 and 1. But in case of the ReLU, all the negative inputs are transformed to 0 and all the positive inputs are passed as it is. So then we can represent a neural network with these perceptrons. So for example, what has happened in case of the perceptron, these are the inputs, and these inputs are passed to a perceptron, and then there are non-linearity, it will produce us the output. But now we can have multiple perceptrons. Why we can have multiple perceptrons? Because we can have different weights for the different perceptrons. And when we are going to combine these perceptrons with some non-linearities or activation functions, then basically it becomes the neural network. And then all these nodes will be termed as the neurons. So now here you can see, basically we are having now the neurons, and these input layer means this is basically the dimensionality of the data. These are the input features which is coming in. So this is x1, x2, x3, and xd. And now what happens? Now we can have a hidden layer. So in case of the perceptron, we directly fed the input to this perceptron, and whatever is the output of this perceptron is the final output. But right now what we are saying, we can have one more layer before producing the final output using this perceptron. And then what that layer will do, that layer will transform these inputs, means it will consider the original inputs and produce some outputs. And then final neuron that we have in the output layer will make use of the output of all these neurons, which is in the hidden layer. And the processing mechanism will be same for all these neurons. All these neurons will do the similar computation, means it will receive the inputs from all the nodes from its previous layer, either input layer or hidden layer. Suppose if you are processing in the hidden layer, then it will consider all the inputs in the input layer as the inputs to this particular neuron, and then it will have associated weights w1, w2, w3, w4, and ultimately we will perform this w dot x, and even we can have a bias term for this neuron. Then w dot x plus b, we can have some non-linearity with this neuron like ReLU or any other activation function. Then after passing to that function, whatever is the output, that will be passed to this output layer. Then we can write like this. So we can write z w11 transpose x here. So x is the original input, means x1, x2, x3, x4. In this example, it is 4-dimensional, but we can assume d-dimensional. Or even we can assume k-dimensional, because in this particular example here we are representing up to k. So now we can write these parameters like w11. All these parameters can be written as w12. All these parameters can be written as w1k for the last one. Ultimately, combining all together, we can say this is w1x, where w1 will become basically parameter matrix, because it is combining all the parameters of all these neurons. And then we can get the output of all these neurons, which is in the hidden layer, and it will become the input to the neurons, which is sitting in the output layer. So then final output now can be given as z, which is some activation function, and there will be weights associated with this output layer also. So that is w2. So w2 transpose output of the all neurons in the hidden layer, which is represented as zw1x. Okay, then question comes that what these neurons would be doing here, means now we can have any number of neurons. Suppose someone is having 2 neurons, 3 neurons, 4 neurons, 5 neurons, and obviously it becomes a design choice for us that how many number of neurons we want to have. And basically, whenever you are going to build a neural network, you have to specify that suppose if you are having a hidden layer, then how many number of neurons you are setting in that hidden layer. And this is basically called the forward basically pass of the neural network, when you are feeding your input from the left side, and ultimately you are getting your final output from the last output layer. And basically it can be termed as feed forward neural network, because we are basically feeding the input from the left side, and ultimately it is passing through all the layers that we have from left to right, and the rightmost layer that we have will give us the final output. So what happens, because with all these neurons that we have in the hidden layer, they are also equipped with some non-linearity. For example, this G that we have. So non-linearity means it will transform whatever output, whatever w dot x we will get, it will transform that value in a non-linear through a non-linear function. And suppose if that is ReLU, then or even if you are using sigmoid, then it will transform those inputs using that particular function. So what happens now? Basically, the number of if the number of neurons in the hidden layer is more, then the amount of non-linearity that we are introducing in this neural network will be also more. And when the amount of non-linearity will increase, then the capability of our neural network to handle even a non-linear data set will increase, because what happens if we are having more and more non-linearity, then we can transform our non-linear data in such a way that it can become linearly separable uh, in the final feature that we are getting just before this final output layer, or basically just before the classification layer. So here is a pictorial representation with some distribution of the data. So you can see these blue ones and red ones. So there are blue dots and red dots. Blue dots and red dots, they are basically mimicking the data distribution for two categories. And what what we are showing here, suppose when we are having only 3 neurons in the hidden layer, then in that case, what kind of decision boundary is being learned by the neural network? So here you can see it is able to learn the nonlinear decision boundary. Now, in the linear classifier, if you consider, when we had only a hyperplane, that hyperplane was a linear classifier, and the decision boundary between two categories was also a linear function. But when we are having nonlinearity, then our decision boundary between two classes will also become nonlinear. And that's where we can see in the leftmost figure here. Now, this is the decision boundary between these two categories, and this is nonlinear. But the nonlinearity in the decision boundary is still restricted. Even we can find out some red dots which are not actually coming in this the category which is figured out by this decision boundary for the red category. So some red dots are outside of that, or some blue dots is outside of that blue category. And it means that even we have the nonlinearity, but that is not sufficient to accurately represent our this training data set distribution for these two categories. But if we increase the number of neurons, for example, suppose if we go with the 6 hidden neurons, then the nonlinear capability will increase. And now here you can see some of these red dots are now even coming, which is inside this red region here. And if we further increase, suppose 20 hidden neurons, then even we can basically go with the overfitting, where all these samples which belongs to the red category are actually belonging to the red one. Even a two-layer, there is a theory which says that a two-layer neural network can be also seen as a universal function approximator. It means that we can transform the data from one form to another form with whatever nonlinear complexity we have. But given that the number of neurons that we have in the hidden layer, there is no limitation on that. If we are allowed to use infinite number of neurons in the hidden layer, then even we can use that neural network to basically approximate any function that can exist in the universe. But what happens? What will be the problem? If we have many number of neurons, then computational complexity will increase and it will become infeasible for our machines to do that computation. So there are some questions. What is the role of bias function? Okay, so role of the bias function is basically to perform some shifting. So even if you consider, if you just consider a equation of a line y is equals to mx plus c, so you know what is the role of this c, that intercept. So the similar role you can consider for this bias even in neural network. And we will also see later on when we will see regularization, maybe not in terms of bias, but in terms of weights. Is neuron same as non-linear classifier? So neuron means just doing some computation. And what is that computation? The computation is w dot x, means whatever input you are receiving to that neuron is x, it will have the parameters which is w, and it will perform w dot x. And if you are having some activation function with that neuron, then it will transform that output through that activation function. Then ultimately a neuron is generally termed as a nonlinear transformation, because first we perform the linear computation w dot x plus b, which is linear computation. Then that output will be passed through a non-linear function, which is generally considered as part of the neuron. It is basically to just introduce the non-linearity in the entire network. Could you please repeat what is happening in the hidden layer? So what is happening in the hidden layer? Basically, if you see different neurons in a hidden layer, all these neurons are receiving the same inputs, but they will have different weights. So ultimately, a hidden neuron is nothing but it is trying to compute the weighted sum of the inputs. Now, what will be the weight? That weight will be decided based on some optimization technique that we will see later on. But whatever is the current weight values, using that current weight values, it will do the uh, weighted summation of these inputs. Ultimately using these neurons, what we want to do, we want to explore different possibilities of combining the input values that could be meaningful to solve our task. And why we want to combine this? Because we want to also find out what is the correlation between different dimensions of the input that we have. We want to better utilize that. We want to better utilize the correlation between all these different inputs, and not just between the different features of the same input, also different samples, because we will see later on, we actually do the batch wise processing when we do the training of the neural network. So but at the end, what this hidden neuron is doing, it is basically trying to project your data from your input space to some other space by combining that data in a weighted form. That weight through which it will combine, it will be basically learned from the network automatically. So do not understand the output of the hidden layer. The output of the hidden layer is nothing but a number, which is again the combination of the inputs, that we different features of the inputs, which is weighted by the weights that we have. What is practically a neuron? So a neuron is nothing. Neuron is basically the computation that we are doing. So what we are doing here, w dot x plus b, that's what we are saying. This is a neuron. So neuron, like we are showing a circle as the neuron. There is no circle is existing when you are going to implement. So what happens? This is basically just as a notion here. When you are going to implement it, then you will say that suppose we are having a hidden layer, and in hidden layer, if you are saying there are some k number of neurons, then based on that you will basically you will initialize that many number of required weights. So for example, suppose in the hidden layer 1 here, suppose you are having 4 neurons, and in the input layer you are having 3 features. So now how many number of weights will be required? For the first neuron, we need 3 weights. For the second neuron also we need 3 weights. For the third neuron also we need 3 weights. For the fourth neuron also we need 3 weights. So 3 into 4. So what we will do, basically we will generate 4 random values, and we will consider those 12 random values, and we will consider those 12 random values as the weights for these neurons, and we will do the computation accordingly. Hinge loss trains classifier. Yes, hinge loss is also one of the loss which trains classifier, and hinge loss is nothing but this is SVM loss, or the max margin loss. So right now we are not focusing on the hinge loss part, because that is a completely different thing. SVM itself will take a lot of time if we go in deeper. So I will show a demo also of this neural network, means how basically this computation is happening through a visualization shortly. Okay, so now we can have even more than one layers. For example, here we are having 2 layers. So this is hidden layer 1 and hidden layer 2. So what is the difference? The only difference is we are having this new layer, and then any neuron in this new layer will receive the inputs from all the neurons in its previous layer. Means the output of these neurons in its previous layer will become the input for all these neurons, and they will also have their own weights. So again, this neuron will have 4 weights, this neuron also will have 4 weights, this neuron will also have 4 weights. They will again have the weights, and they will also do the computation in the same manner, that is w dot x plus b, and then it will be passed through some non-linearity, and that will become output of the neuron in this particular layer. So like that, we can have any number of hidden layers here, and the number of neurons in these hidden layers also we can have different number of neurons in the different hidden layers. So it becomes basically a deep pipeline where we have different layer and inputs are being passed from left to right side, which is passing from the different layers. And it basically ultimately it learns a feature hierarchy. And we assume now that all these layers are slowly trying to transform our input data in a different way, such that at the end, whatever final feature we will get after the last layer, that will become very abstract feature. It will have the information which is very relevant to the problem that we are solving, and other information which are not relevant to our problem will be slowly discarded in between this in this pipeline from left to right. And if we feed that final feature that we get to the softmax classifier, then it should basically perform very well. So when we are designing a multi-layer neural network, then obviously there are several hyperparameters that comes into the picture, and that we need to decide manually that what should be. For example, how many layers to be used. So we can basically have a long discussion on this, that how to decide how many layers to use. So again, there is no fixed rule. Mostly people are getting to know all these things from the practice. When people are solving the problems, they are using different neural networks, then they are observing what is the performance. Based on that, they are getting some idea that, okay, if I'm solving this problem, my data set is like this and complexity of the data set is this one, then what should be the approximate number of layers that I should use, or number of units per layer that I should use, or which activation function to be utilized, which loss function to be used. And regularize overfitting is a very challenging part in neural networks. So which regularization technique to be used to overcome the overfitting part, and what is the regularization constant, which optimizer to use for the training purpose. Because in SGD itself we are having different optimizers, like you people might be knowing Adam, which is very popular nowadays for as a choice of the optimization technique. And even in optimizer also, what should be the learning rate, what should be the learning rate schedule, how many number of epochs that we should use for the training purpose. And if the training is happening in the batch wise fashion, then what should be the batch mini batch size. So there are many such hyper parameters that comes into the that basically has the role, and that we can decide based on some observations. Usually you get either from uh, some reports, or even mostly you will get from your observation. If you are trying to solve the problems and implementing, then you can get to know these things in a much better way. So what is optimizer again? So optimizer is basically how we will update the weights, that is W's and B. So if you again remember, we have W dot X plus B. And so far, what I have assumed that we already know the right values of W and B, but that is not the case. When you are going to solve a problem, you are having the data and you are having a network, you are having parameters in the network, but you don't know what should be the right values of W's and B. So how we will get to know what should be the right values of W and B? So what we do, basically we pose that problem as the optimization problem. And usually in deep learning there are several ways to solve this, but usually we utilize stochastic gradient descent, where we initialize those parameters randomly, and then we do the forward pass and do the backward pass. And in the backward pass, we compute the gradient of our loss function with respect to the parameters of our model. And then using that, we update the values of the W. And this entire process is called optimization. And the way we are doing this, that is governed by some algorithm, and that algorithm is called optimizer. So for example, stochastic gradient descent itself is the optimizer. So this is what will happen if we change the regularization constant. So obviously, when you are dealing with neural network, you're having data set, you have to design your neural network. It can have different number of layers, different number of neurons in different layers, then complexity will be different. So we can have a simple model, we can have an intermediate model, we can have a complex model. Based on that, based on complexity, and based on complexity of the model and complexity of the data set, we can basically figure out what could be the bias and variance. So, or what could be the scenario for the overfitting and generalization. So for example, suppose if you are having a very simple model, then it is possible that it may not be able to perform very well even on the training data. And that's what you can see in the left side. So our model in the left figure is almost linear, and when it is almost linear and data is not linearly separable, so in that particular case, obviously all these training samples of the red ones, which is at the upper side, it will be misclassified by our this model, and the performance will be down. Intermediate model, that's what actually we want, where the performance should be also good, but at the same time we should not be overfitting. What is meaning of overfitting? That you can see in the right figure here. So this is overfitting where our model becomes too complex such that it can find a decision boundary in such a way that it performs roughly 100% on the training data, close to 100%. But in that case, what happens? Its performance may degrade on the test data, because what happens? Suppose if we are getting even a test sample which is very near to these red ones, but this red one itself is noisy here because it comes in an island of these blue ones, then the training data itself is the noisy, and it consider that particular training it as part of the training sample, and based on that it finds out the decision boundary. So all the test sample which might be near to a noisy training sample of other category, that will get misclassified, and then basically generalization capability will go down of such models. So based on that, we generally get two terms, which is called bias and variance. And what happens in the left side, it is having very high bias and very low variance. So whenever a model has high bias and low variance, it means that our model is underfitting. Underfitting means its complexity is very low, and even it is not able to perform very well even on the training data, and we need to increase the complexity of our model. And when we have the low bias and high variance, then in that scenario signifies that our model is very complex and it is overfitting. And in that case, basically we need to look for the generalization aspect, and that's what we will see in the second part. So what if your model is bias is too high, that is underfitting? We need to basically increase the complexity of the model. That's what we need to do. And that is also that is also representing underfitting. If it is having very high variance, then that is overfitting. How we can recognize it is underfitting or overfitting? That we can recognize from the error plot. If the loss on the training and test set both are very high, that is underfitting. If the loss on the training set is low, but the loss on test is very high, then that basically signifies the overfitting. So we will have a more detail on this particular aspect in the second part. Okay, because there was a lot of questions on the optimization, so let's have a quick look on the basic optimization aspects, and then we will see optimizers in detail later on. So optimization means what? Optimization means we want to find out some strategy to figure out what should be the right values of our parameters, that is W's and B's. And because these W's and B's, they are already there even in a linear classifier, and even they are also present in the multi-layer neural network, where we are having W's in each layer, means parameters in each layer are present. So one thing we could do, random search, we can let's randomly assign all these parameters. Let's see how well it is performing. Next time again initialize all these parameters randomly, and let's see what is the performance. Next time again initialize randomly, and let's see what is the performance. But if we are doing like this, then we are not utilizing any knowledge that our model is gaining from the previous step, and that is not going to be a good approach. Then instead of doing this is global random search, we can do the local random search, but again we will end up with the same problem. So then what happens, basically the idea that we can exploit is to follow the gradient. And how we can follow the gradient? So what we can do in the gradient descent optimization technique, suppose if we are having any parameter W, then the parameter W will be updated as W minus learning rate. So this is learning rate multiplied with the gradient of that parameter W with respect to the loss function that we are using. Okay, so what is meaning of this? This is basically the updating of W in the opposite direction of the gradient. Why in the opposite direction of the gradient? Because we know, suppose if you are having any function, and if you compute the gradient of your function with if you compute the gradient, if you compute the gradient of any parameter, then what information it will give us? It means that it gives us the direction where the changes are happening mostly. Okay, so it means that if we go in that direction, if we go in the direction of the gradient, then our output will be maximized. That's what will happen if we follow the gradient. But here, what is our objective? Our objective is to minimize this loss function, minimize the loss value. Means we want to minimize the error. Our objective function is designed in such a way that it is giving us that how bad our model is performing on the training set. So it is giving us the loss value, and we want to minimize that loss value so that it should become zero. So because this is a minimization problem, that's where instead of updating our parameter in the direction of the gradient, what we used to do, we update in the opposite direction of the gradient. And that's why we are having W minus here. What is this learning rate here? Learning rate is the step size. We are saying that, okay, you update your W in this direction. But when we are updating our W in this direction, that how far we should update, what should be that size, means how long, what should be our step. So that's where basically this is also called learning rate or step size, which is manually again being set. Usually we used to set as 10 to the power minus 2 or minus 3. This is going to be usually a smaller value. Why this is going to be a smaller value? Because we are updating based on the gradient information, and gradient itself has its meaning when we are basically doing the operations for a very small displacement. If our displacement is very large, then gradient information will not hold for such type of computation. Then in gradient descent, what is happening? Basically, we are having the weights. We update the weights in the opposite direction of the gradient. And how we get the gradient, that for that we have a chain rule, and I will come to that, how we'll compute the gradient using the chain rule. And usually we perform the mini batch gradient descent, where the gradient is computed as the mean over a set of the samples, which is fed as the input as the batch of the data. So interpretation of the gradient, we can represent gradient like this, dfx by dx as the limit h tends to 0, fx plus s minus fx divided by h, we know from our calculus. Suppose if we have a function fx y is equals to x plus y, and we want to compute the gradient here. So basically we do the partial derivative. So in this case, it is very easy to say del f by del x is 1 and del f by del y is also 1. And suppose if we have x into y, then del f by del x is y and del f by del y is x. Suppose if we are getting even a max function like max x comma y, then in that case, what will happen if we do the derivative, partial derivative? So del f by del x, it will be 1 if x is greater than y. X is greater than or equals to y. Otherwise, it will become 0. Means if the maximum of x comma y is x, then del f by del x will be 1 and del f by del y will be 0. But if maximum of x comma y is y, then del f by del x will become 0 and del f by del y will become 1 in that case. So here it is representing 1 into this condition. So if this condition is true, then 1 into 1. Otherwise, if this condition is false, then 1 into 0. So here also 1 into, if this condition is true, then 1 into 1, otherwise 1 into 0. So we can also, because again from the calculus, we know that if we are having the compound expression, then we can use chain rule in the calculus to compute the gradient of our function with respect to any of the parameters that we have here. So here we can see we are having three parameters, x, y, and z, and our function is x plus y into z. So actually we can write this x plus y into z into a two-layer transformation mechanism. In the first layer, we are computing x plus y, and whatever output we are getting of x plus y, that is represented by q here, that will be used along with z in the second layer to compute f. Suppose if this type of setup is there, then how we can get the gradient? So in this case, because these are basically the single layers. So for single layers, we can get the gradients directly. So del q by del x we get as 1, del q by del y also we get as 1, del f by del q we get as z, del f by del z will become q. So if we can get this, then using chain rule, we can get del f by del x, because at the end, what we are interested to compute? We are interested to compute del f by del x, del f by del y, and del f by del z. So now we can compute del f by del x as del f by del q into del q by del x. If we know del f by del q and del q by del x, then we can get del f by del x using this chain rule. So we can represent the same thing as a computational graph. So here x, y is the input, then we are doing the summation, output is q, z is the input, q into z is going to be f. So in this particular computational graph, we can do a forward and backward pass here. So what is this forward pass? In forward pass, we are having these inputs and we compute what is the final output we will get. So -2 plus 5 is going to be 3, 3 into -4 is -12. What is the important thing here? How we compute the gradient in the backward pass. Once we get the gradient, then updating the parameter will become very easy. Then updating the parameter is just update in the opposite direction of the gradient with a step size or learning rate. So suppose if you are passing the unit gradient, then what will be the gradient? Means now we are interested to compute here del f by del x, del f by del y, and del f by del z. But because this particular second function here is f is equals to q into z, so we get del f by del q and del f by del z, and del f by del q will become basically -4, and del f by del z will become 3, because that is a multiplication function. So this is 3 and this is -4. And once we have this del f by del q, and we are interested to compute del f by del x, but we have del f by del q, then how we can compute del f by del x? So using chain rule, del f by del x is nothing but del f by del q into del q by del x. And we have already computed del f by del q, which is -4. So if we just compute the local gradient, which is del q by del x, then we can multiply this local gradient into the running gradient, which is del f by del q. And then we can get del f by del x. That's what we wanted. So, and local gradient del q by del x, because this is a summation function, so del q by del x will become 1. So ultimately del f by del x is equals to -4 into 1, so it will remain as -4, and the same thing will become true for y also. Let's again take another example with some other function in order to understand this forward and backward pass. Now suppose we are having x, y, z, and w. These are 4 inputs. We are doing x into y and taking max of z and w, and then whatever output we get, do the summation of this and then multiply by 2. So for these inputs, doing the forward pass, 4 into 3 -12, -4 into 3, max of 2 and -1 is 2. So now -2 plus 2, that will become -10, and -10 into 2 will become -20. So this is a forward pass. In the backward pass, what we do? Let's pass the unit gradient and let's see how much we will get. Suppose if the final output is f, then the del f by del x we need to compute, del f by del y, del f by del z, and del f by del w. So now what we will do, we compute the local gradient and multiply with the running gradient. So that's what is actually the chain rule. So what is the local gradient here? So local gradient is, this is basically a function like y is equals to 2 times x. So what will be the gradient for this? So the gradient for this will become 2. And when gradients for this will become 2, and gradient is independent of the input, so 2 into 1 will become 2, and that's what will be the gradient that will be passed back here. So 2 will be passed. Now, again, if we see this function, let's consider this local function. So this local function is like this, z is equals to x plus y. So suppose if this is x and this is y, then this is z. So this is z is equals to x plus y. In that case, del z by del x will be also 1. Del z by del y will be also 1. Means local gradient for both the branches will be 1. So what will happen? We will multiply that local gradient with the running gradient. Running gradient is 2. So 2 into 1 will become 2 and 2 into 1 will become 2. So 2 will be passed as the running gradient now to both the branches here, 2 and 2. Now let's focus on the top one. This is the multiplication function. It is like z is equals to x into y. And we already know what is del f by del z here. Del f by del z is 2. And we are interested to compute del f by del x. So del f by del x is equals to del f by del z, which is 2 into del z by del x. And del z by del x will become the local gradient. And because this is a multiplication function, and then local gradient del z by del x will become y, and y, the current value of y is minus 4. So the local gradient will become minus 4. So minus 4 into 2 will become basically the final gradient for x, that is parameter x. And then it will become minus 8. Similarly, we can compute for y. So local gradient will become the value of x, which is 3. So 3 into 2, that becomes 6. In the bottom one, we have the max function. So if we remember the gradient mechanism for the max function, if 2 is passed, then the local gradient for this branch will be 1 and local gradient for another branch will be 0. So, and 2 is the running gradient. So 2 into 1 and 2 into 0, that's what will become as the gradient for these parameters z and w. So now this is a very interesting thing. So we are saying that del f by del w is 0. And suppose if you get a gradient 0 with respect to any parameter, what does it mean? It means that that parameter does not has any influence on the final output that we are getting. And that's what is happening in the present scenario here, because the value of the w is discarded just after this max and it is no longer utilized in getting the final output. And that's why we are getting this gradient as 0. This is another example. I am just skipping this particular example. So as we have seen earlier, this is the perceptron. And in the perceptron, if we use the sine function as the nonlinear function, then this perceptron itself can be utilized as the binary classifier in the supervised learning. Because then w dot x plus b can be represented as basically a hyper this classifier that we have seen in case of the linear classifier. And we can basically just get the sign for these two categories that we have for this binary classifier. And a single neuron, if instead of utilizing the sine function, if we utilize a sigmoid function as the nonlinearity in a single neuron, then basically because sigmoid function outputs everything between 0 and 1. So which can be considered as a probability. So it means that the output of the neuron can be treated as the probability of being classified into one of the classes. And then it can be also utilized for classification purpose. Then, but this particular approach, which is called logistic regression, it is much better than the binary classifier, because in case of the binary classifier, the last layer is the sine function. Then what will happen? If you want to train such model using gradient descent, then your gradient will not flow back. Local gradient will become 0 for the sine function, and you will not be able to train such a model. But if we have a logistic regression, then logistic regression still has the gradient. So we will pass the gradient back in the back propagation and we will be able to train the model. So this is just loose inspiration of the neurons that we have seen. Means what is the biological neuron also has some computational unit, and it has basically the activation which transform the outputs into using some nonlinear function, and then it will be passed as through the axons to some other neurons. It will become inputs to other neurons. So this artificial neural network is also trying to mimic this, but not exactly the same thing. So can you please explain forward and backward pass. Okay, so what is forward pass? In the forward pass, we are having the input, we are passing that input from each of the layer, and ultimately at the end we will get the class scores. Then that class scores will be also used with as the input to our softmax classifier, and our classifier will be using cross entropy loss, we will finally get the loss. That is the forward pass. What is the backward pass? In the backward pass, we start from the last layer, we compute the gradient for that, and then we pass that gradient to its previous layer, we compute the local gradient for its previous layer, and because we have the running gradient, then we get the gradient of our final function, final loss function, with respect to the parameters in that layer, and then we update those parameters. Means suppose if parameter is w, then w is equals to w minus learning rate multiplied with del L divided by del W, means the gradient of the loss function with respect to that parameter. And we do this process for each of the layer from right to the left in the backward pass. How to pass to the previous layer? I will show it mathematically, how to pass to previous layer. Calculation also I will show mathematically these calculations. Okay, so let's consider a multi-layer neural network, and even we can compute how many number of neurons and parameters we have in case of the multi-layer neural network. So here is an example. Left side, only one hidden layer, and how many number of neurons we have? 1, 2, 3, 4. We have only 4 neurons. That is not counting the inputs, because inputs are not neurons. They are basically just our features of input. So we have 4 neurons in the hidden layer and 2 neurons in the output layer. So the total number of neurons are 6. How many number of learnable parameters? Learnable parameters means those parameters which that we are going to update in optimization. So how many learnable parameters we have? So this one neuron here, there are 3 connections, means 3 inputs. So there will be 3 parameters. And we can have one bias also. So 4 parameters, including bias. And 4 parameters for all these neurons. So 4 into 4, 16. Similarly, if we go to the output layer, then one neuron in output layer is connected to 4 inputs, then 4 parameters plus one bias, 5. 5 into 2 is 10. So 16 in the hit is 26. So 20 weights. Out of that, 20 will be the weights and 6 will be the bias. Computing number of bias is very easy. That is exactly same as the number of neurons we have. That means number of bias will be there. Similarly, we can compute for the second one also. So I'm not going to compute in detail, but it comes to 9 number of neurons, and total number of parameters will be 41. Okay, now let's have a quick demo here that how this multi-layer neural network is actually working. So let me go to this. So I hope this browser is visible. So this is a very nice interactive environment built here where you can basically test with neural network by changing the different things that you can see in neural network. So here you can see we are having some data distribution you can see at the right side. So this is our data distribution which is there at the right side. And basically this is a 2-dimensional data. So we are having x1 and x2. These two are basically the inputs that we are having. And we have 2 hidden layers in this case. And the first hidden layer has 4 neurons and the second hidden layer has 2 neurons. And what we can do, we can increase and decrease the number of hidden layers. So here on the top, you can see we can include one more hidden layer, or we can decrease the hidden layers from this. Suppose I'm keeping 3 hidden layers. Even in a particular hidden layer, we can increase or decrease the number of neurons. So here, if you see, we are having 4 neurons. Even if I want, I can have 3 neurons. In the middle ones, suppose I want to have 5 neurons. In this one, I want to have 4 neurons, 3 neurons. So like that, we can change the number of neurons and the number of hidden layers in this. So We can also set the learning rate. Suppose learning rate I am going to set as 0.03. Which activation function you want to use? Suppose I am setting ReLU. And which regularization? Right now I'm not talking about regularization. Suppose classification problem. And after that, what we are going to do, we will start the training. And once we will start the training, then how decision boundary is being learned, that will be basically displayed here in the right side data distribution that we have. So here you can see once we started the training. So now you can see this was the decision boundary which was basically being learned. And now you can see this is a nonlinear decision boundary. Why this is nonlinear decision boundary? Because with all these neurons, we are using the ReLU activation function. But suppose if we don't use the ReLU activation function, for example, if we make the activation function as the linear function, I have changed here this activation function as the linear function. In that case, because there is no non-linearity, we cannot get the non-linear boundaries. We will get only a linear function as the boundary. So in that case, suppose if I again train, then what will happen? Even though I am training, now you can see I'm not getting any non-linear decision boundary. Rather, I'm just getting one line here. If you see, this line is trying to distinguish these two things, but that is not working well. And that's what you can see from the loss also. Loss is very high. Even the training loss is also very high. That is 0.498 because in a linear classifier cannot basically divide these two categories. That is not possible. Even we can introduce some noise here. So for example, suppose if we are introducing this noise, so now you can see even some these red ones are coming in between the blue ones. And again, suppose if I use ReLU activation function and if I start training, then what will happen now? Our model will try to be overfitted over a time. If we train it longer, it will try to be overfitted such that this nonlinear decision boundary will be also learned in such a way that all these red points slowly become outside of this, which is even inside, because these noises will be also considered as part of the data. Okay, how to understand whether to use linear or non-linear beforehand? So that basically you have to judge from the complexity of your data set that you have. Suppose you want to do the classification of human versus animals, then that is a very simple problem. There you can have a linear classifier. It can even give you the good performance. But suppose you want to do the discrimination between cat and dog, now a linear classifier may not be able to work very well, because many cats will also look like dog, many dogs will also look like cat. Means when you are going to do the fine grained classification, or when you are going to have the samples of different categories looking similarly, and samples even within the same category looking very differently. For example, suppose you have chair. Now someone can even in the chair also itself we can have a very different type of chairs. Then there could be a lot of variability within the class itself, and there could be between different classes. When these two things become very high, then our problem becomes very complex, and their linear things will not work, and we have to go for the non-linearity. How can we go for this page? Basically, okay, I will provide the link here. Just remind me at the end of the session. Okay, so now let's close this. So I hope, I think we are basically going over the time. Maybe we can stop here and we can continue in the second session, the remaining part.
Thank you so much, sir, for this wonderful session. I'm Samir Jain on behalf of Asia Connect. I'm thanking you for this wonderful session, especially for the insights that you have given that is related to the back propagation, because that is very, that should be understood by everyone before they are going to apply some machine learning based problems, especially on neural networks. So thank you so much, sir.
Okay, thank you very much. So we will again start in next 20 minutes.